So far we have discussed about the momentum equation and its applications. Today we will discuss about the energy equation. By energy equation, what we mean is that we want to conserve the total energy of the system. So, if we write the Reynolds transport theorem, if we write this, then for the total energy conservation, capital N should be equal to E, that is the energy of the system. Remember, this is the total energy as per the purview of the laws of thermodynamics. So, that means this is the sum total of internal energy, kinetic energy and potential energy. That is what we are talking about as the total energy. Now, when capital N is equal to the total energy, small n is the specific energy, that is the total energy per unit mass. So, you can write we will further assume that the control volume is steady and control volume is stationary, not steady. And control volume is non deformable. So, the stationary control volume implies that the relative velocity is same as the absolute velocity, and non deformable control volume means you can take this time derivative within the integral. So, that means you can write Now what we will do is we will express this in terms of the first law of thermodynamics. So think of a system or a control mass. The first law of thermodynamics in a rate expression can be written as, if you say that the heat transfer to the system is Q dot and work done is W dot, then Q dot this is the first law. First law for a system. Therefore, you can write dE dt is equal to Q dot minus W dot, and this is Q dot system minus W dot system in the limit as delta t tends to 0, the system tends to the control volume. That is how we derive the Reynolds transport theorem. Therefore, this will tend to Q dot Cv minus W dot Cv, where Cv stands for the control volume. So here in the left hand side we have expressed it in terms of the heat transfer and the work done. Next, our objective will be to write the expressions for heat transfer and work done. First, let us write the expression for heat transfer. Just like in continuum mechanics, you have two types of forces, surface force and body force. Similarly, heat transfer you have two types, one is surface heat transfer and another is volumetric heat transfer. So let us say let this be the heat flux and so Q dot Cv this is heat generation per unit volume. So you multiply it with the elemental volume and integrate it over the control volume. So this is for the volumetric part. For the surface heat transfer, you have to keep in mind that if we have a heat flux like this, this is actually a negative heat transfer, because heat transfer to the system or to the control volume is positive as per the first law sign convention. I mean, we could also make a different sign convention, but while writing this we have made this sign convention only. So this will be adjusted with a negative sign we can write this as by using the divergence theorem we are converting the area integral into the volume integral. Okay. So, this is for the heat transfer. Next, let us find out what is the work done. Now, in mechanics when we write work done, we write work done by the force as positive, and in thermodynamics you have work done by a system against a resistance is actually a positive work. So, that means again we have a conflicting sign convention. To adjust to that, we will write in terms of mechanics whatever is the expression for work done, when we substitute it in the laws of thermodynamics, same expression but with a negative sign. So, now work done is because of what? Because of surface force and body force, right. Work done is because of presence of forces, and there are two types of forces, surface force and body force. So, work done is due to what? Work done due to surface force plus work done due to body force. The surface force work done due to surface force. Now, let us say that this is a control surface. Let us say that you have an area dA. What is the force per unit area on this? Recall that that is nothing but the traction vector, this is force per unit area. So, this times dA is the total force, and work done is the what? The dot product of force and velocity, rate of work done, right, W dot, that is the dot product of force and velocity. So, this will be integral of this vector dot with velocity vector, that means Ti ui dA, right. Dot product of two vectors means basically multiplying their individual components and summing up. So, if there are two vectors A and B, their dot product is Ai Bi, right. So, you have Ti I will adjust the sign later on. Without the sign I am first writing the expression. Plus rate of work done due to body force. Body force per unit volume, we when we derive Navier-Stokes equation, we assume body force per unit volume is B. So, Bi ui dV. This is B dot E, B dot velocity, B dot U. So, basically we will write this as minus of W dot Cv to adjust for the sign. or W dot Cv equal to minus of this, whatever. Now, what is Ti? Ti could be written by using the Cauchy's theorem. So, Ti is this tau ij eta j, right, Cauchy's theorem. So, this you can write as right, just another way of writing this. Now, Ti ui dA so let us give this a name tau I. So, how can we write this? Del dot tau I ui, that means in index notation del del xj of this is just another way of writing del dot tau I ui. So, now you can write so, we will now substitute that expression here. In the dE dt system, it is q dot minus W dot. So, we will substitute the Q dot and minus W dot. So, Q dot Cv minus W dot Cv. Q dot Cv is integral of this I am deliberately trying to mix up notations and symbols so that you get familiar with different types of symbols. Of course, this could be written as del del xj of qj, right, same thing. This is heat transfer minus W dot Cv is Now, let us come to the right hand side. So, left hand side all terms are expressed as volume integrals. Let us express right hand side all the terms also as volume integrals. So, right hand side what is this term? Del dot rho EV or del del xj of rho E uj, right. So, this is del dot rho EV. So, now we can write right hand side is equal to left hand side Okay. So, all term expressed as volume integrals. So, this is as good as writing integral of something into dV equal to 0. Since the control volume is arbitrary, this is as good as this something is equal to 0. So, that means you can write now the left hand side, what form is this? Is it a conservative form or a non-conservative form? This is a conservative form because we started with the basic conservation equation. We can convert this into a non-conservative form by using the continuity equation. So, let us do that. So, what we have done is we have used the product rule of derivative. Now, we can write this is equal to rho by combining these terms and plus E So, this is 0 by the continuity equation. So, this becomes rho so if it is written in this way, then that is the non-conservative form of the equation. We have to keep in mind, again I am repeating, although rho is coming out of the derivative, that does not mean that rho is a constant. Rho is coming out of the derivative because of simplification using the continuity equation. Now, this equation physically what does it represent? It represents the conservation of total energy in a control volume perspective. Now, in heat transfer we are interested in conservation of thermal energy. So, if you have conservation of total energy, how can you get conservation of thermal energy from there? So, in the total energy you have mechanical energy plus thermal energy. So, you have to write an expression for conservation of mechanical energy. Mechanical means kinetic and potential. So, what essentially is this? This is kinetic plus potential plus internal. So we have to write something in terms of the internal energy only. So we have to subtract the equation that involves kinetic and potential energy, that is the mechanical energy equation. Now one has to be careful in one thing. In this equation, when we write E, actually we are including within it the internal energy, kinetic energy, but not potential energy. Why? Because we are already having an expression for work done by body force. So if we now again write potential energy here, then that will duplicate the same effect. So either you do not write the work done by body force, but put the corresponding potential energy here, or you do not put the potential energy here, but you put the work done by body force. So here we have preferred to write the work done by body force, therefore we will not include the potential energy here. Okay. Now work done by potential energy, if it is not included, at least work done by in the energy, if the potential energy is not included, that means work done by body force is already included, then which equation will give you the mechanical energy? So this equation has given you the total energy, where you have somewhere the potential energy effect and internal energy and kinetic energy. We will want to get another equation which will give us the mechanical energy equivalent of the work. So mechanical energy, that means the kinetic and the potential will be in form of work done by body force. So which equation can give us? Navier equation, what was it? It was an equation of momentum balance. So in a conservative form, rho this equation, why we start with the Navier equation but not the Navier-Stokes equation, is that we want to generalize it for all types of fluids. So once we commit ourselves to Navier-Stokes equation, we are restricted to Newtonian and Stokesian fluid. But when we write the Navier equation or the Cauchy equation, whatever, we are not bothered about what is the special type of fluid that we are talking about. So for any fluid you can use this. So now can you convert this momentum balance equation into an energy equation? Only a small trick you have to play to do that. See, you want to convert it into mechanical energy equation, that is kinetic energy and potential. Potential will be work done because of the body force. So how can you convert this to kinetic energy? You multiply this with ui. So then it becomes ui del t, the other is del t of ui square by 2. Ui square by 2 is kinetic energy per unit mass. So you multiply by ui. So rho let us say this is equation number 1, this is equation number 2. Now if you subtract equation number 2 from equation number 1, what you get? You will get an equation that governs the change in internal energy only, because kinetic, this is kinetic, this contribution is due to potential, and you will see that if you, when you subtract this, E includes what? Internal and kinetic. So internal and kinetic minus kinetic will become only internal. So if you subtract equation 2 from equation 1, we are using the symbol I for internal energy. The reason is that we have already used U for velocity. So just to not to confuse with the symbol, whatever symbol U that you have used for internal energy in thermodynamics, that same is I. If you subtract from this term, then what you will be left? Use the product rule, one term will be cancelled, what will be left is tau ij del uy del xj. So see, the change in internal energy, this is the total rate of change of internal energy. The rate of change of internal energy may be due to volumetric heat generation, surface heat transfer, but also due to stresses in the flow field. So this part, this contribution comes directly from fluid mechanics. So tau ij del uy del xj, physically what does it mean? So this is like a heat source, that means this will result in heating. You may ask that why can't it result in cooling? We will give an answer to that, that it will trivially give rise to heating and not cooling. So it is something like this. Let us say that you have shear in the flow. If you have shear in the flow, then two layers of fluid are sliding against each other. So as if you are rubbing your palms. So if you are rubbing your palms, this work is not utilized, but this work is irreversibly converted into internal energy through viscous dissipation. So this is called as viscous dissipation, where there is an irreversible conversion of work to intermolecular form of energy. So if you rub your palms, you cannot get any work out of that, simply it will generate heat. So that is, so it is effectively like a heat source. So now the question always comes that, well, we are claiming that it is like a heat source, but where is the guarantee that it will always give rise to heating and not cooling? So we have to show that whatever is the effect associated with it, that effect associated with it because of viscous part of the stress. So remember that this tau ij also has hydrostatic part of the stress. So we will isolate the hydrostatic part of the stress and consider only the deviatoric part, which is the viscous part, and show that the viscous part contribution to this term is always positive. That means it will give rise to heating and not cooling. So, let us see the term tau ij. So, we assume homogeneous isotropic and Newtonian fluid. And also Stokesian fluid. So, tau ij is minus P delta ij plus lambda del u k del x k delta ij plus mu del u I del x j plus del u j del x I. This we discussed in quite some length. So, tau I j del u I del x j. What will be the hydrostatic component? Remember delta ij is equal to 1 when j is equal to I. So, it will become minus P into del u I del x I. What is this? This is minus P into del dot V. So, this is like the PDV work in thermodynamics, okay, because the divergence of the velocity vector gives the volumetric change. So, this is analogous to PDV. So, we will isolate that with the viscous component. Remember this lambda is equal to minus 2/3 of mu, Stokes hypothesis. So, plus lambda what is del u k del x k into delta I j into del u I del x I. See del u k del x k is del u 1 del x 1 plus del u 2 del x 2 plus del u 3 del x 3. Delta I j into del u I del x j is del u I del x I. That is also del u 1 del x 1 plus del u 2 del x 2 plus del u 3 del x 3. So, it becomes del u 1 del x 1 plus del u 2 del x 2 plus del u 3 del x 3 whole square, this term, this into del u I del x j. Plus the remaining terms. Plus so here we will write several terms. First I equal to 1, j equal to 2, I is equal to 2, j equal to 1. This is one set. Then I equal to 2, j equal to 3, I equal to 3, j equal to 2. This is one set. Then I is equal to 3, j equal to 1, I equal to 1, j equal to 3. This is another set. Then I is equal to 1, j is equal to 1, I is equal to 2, j is equal to 2, I is equal to 3, j is equal to 3. Total 9, right. So first we will consider this set. So mu del u1 del x1 plus del u2 del x2 into del u1 del x1. Okay, let me write one term, then it will be easier to write. Let me write the full one term. So this is del u1 del x2 square plus del u2 del x1 square plus 2 into del u1 del x2 into del u2 del x1. So it is like a plus b whole square formula, right. So this is mu into okay. So can you physically interpret this? This is like del u del y plus del v del x, rate of deformation. So square of rate of deformation times the viscosity is actually giving rise to a heating effect. Okay. So how the kinematics of the fluid is getting converted into heat transfer effect, that is something which is not so intuitive, but you can see it from here. So this is mu into and this is now what will be this? I equal to 1, j equal to 1 means right. So now it is trivially clear that these three terms together are positive. Of course this term is positive, but this term together with this term, whether it is positive or negative, has to be adjudged. Why? Because lambda is negative, lambda is not positive, lambda is minus 2/3 of mu, where mu is positive. So we will try to show that this term together with this term eventually becomes positive. So let us try to do that exercise. lambda is equal to minus 2/3 of mu. So, if you take 2 mu as common, or 2 mu by 3 as common, so this essentially becomes like, if you take 2 as common, so 3 minus 1 is 2, if you take 2 as common, then it is 4 mu by 3. So, this is a positive term like a square plus b square plus c square minus ab minus bc minus ca, that is half into a minus b whole square plus b minus c whole square plus c minus a whole square. So, this is positive, right. So, our conclusion is that the deviatory component of this will give rise to trivially heating and not cooling, because this entire term, this plus whatever we have written, sum total of this is a positive term, and that term is known as viscous dissipation. Now, our task is not yet complete, because we have written the equation in terms of internal energy, but in experiment we do not measure internal energy, we do not have any internal energy meter. We have say thermometer to measure temperature. So, we have to convert the internal energy based equation to a temperature based equation, which will give us a governing equation for temperature, which is the so called energy equation in convection, that we will take up in the next lecture. Thank you.